Okay, let's start. So today, as you know, I am in Dallas. There is a conference going on and I'm attending that conference. That's why I could not be available today. But the idea is that I will go through some practice questions. Uh, and the topic is still priority queue. So let's look at, NQ and DQ operations, and then we'll look at uh, some questions on priority queues. There are scenarios where priority queues excel, and we'll look at that. That's the last part of the slides. Okay, let me make this larger. So in the last class, what we saw was NQ operation. Here I have written insert P, and that's basically NQ operation on the priority queue, and the new item is P that should go into this max heap. So we looked at NQ algorithm last time, and we looked at how in different scenarios we adjust the heap to be a max heap. But we will today look at the problem from an array point of view, like the array that represents the heap, right? How does it change when a new element is enqueued? So in this figure, you can see a max heap is built. It's a complete tree. The heap property is being satisfied. When we will add P to this heap structure, it will no longer be a heap, okay? And we'll see uh, a bunch of operations that make it a heap again. So here I've listed the indices, so 1, 2, 0 to 10, and there are some empty spots where new elements could go, and the array values are listed here. So let's see, when we do NQP or insert P, then P has to go in the last index, right? So last index from 10 it goes to 11, and we put P here. Now then we have to now look at, is it a valid heap? It's not. P is certainly larger than some of its parent nodes, so we'll see that. So in a heap, we know what are the parent nodes for index 11. So what you can do is subtract 1 from the index. So 11 minus 1 is 10, and divide that by 2. So that gives you 5. So a node at index 11, its parent is 5. So we compare array 11 with array 5. And since it's a max heap, P is greater than C. So that's why we will update the array. So array 5 becomes array 11. So in step number 2, you can see that the array has been modified, right? We did a swap operation. Now, so C moves down, P moves up. Then you again, check if it's a valid heap in the step number 2. So you need to find the uh, parent location for P. So look at the index. Index is 5. That means you find the parent by subtracting 1 from 5, that is 4, and then dividing by 2. So you then go to location 2, right? Index 2. Now you compare H with P. That means you compare array 2 and array 5, and you'll see that P is greater than H. E, F, G, H, I, J, K, L, M, N, O, P. So P comes later, so we again move H to index 5, and then again we compare, what's the root node for P. So P is at index 2, so its root should be 2 minus 1 divided by 2, and that's 0. So we compare Y and P and find out that Y is greater than P, so we don't need to do any updates. So This will remain our final array after insert p. Okay, so let's see if you have any question. Good. So let's now move to next uh, delete operation or a dequeue operation. Okay, so here is the array. This is the same array, right? And we want to dequeue. So dequeue operation on this heap should give us y. That makes sense. Okay, so now let's see a bunch of steps that happen as we remove an item from the heap. There is a hole at location 0, right? This is where y was. Now this, this needs to be made heap again. What has happened is, the candidate that should go to location 0, like the candidate to become the root node of this heap, is the last node, right? That's what we saw in the last class. So R is the candidate and it gets deleted. So we need to delete a node because a dequeue operation is a remove operation. So the number of elements decreases by 1. That's why we removed it. And now it's a candidate to be the root. Now so we also say that it's a hole, right? And for this hole, we find the two contenders and we have a formula for finding two children. So we look at the two children location, and that's 2 into index plus 1, and that's the left, and 2 into index plus 2, and that's the right child, right? So we compare with x and h, and x is greater, so we move x to the location 0. So that creates a hole at index 1. So we repeat this process. So since there is a hole, we need to fill this hole, right? So we will look at the two children for location 1. So for this hole, those two locations are 2 times 1 is 2, so 3 and 4. So index 3 and 4, that's why they are highlighted. So we take G and T. G and T are index 3 and index 4. So we find out which one is the maximum, right? So the maximum is T. So T gets updated here and T moves here. So the hole moves to location 4. So we see a hole here. We repeat the steps. So what are the child nodes? What are the children nodes for this hole index 4? So the formula says 2 into 4 plus 1 is the index for the left node, so that is index 9. So Q is the left child, and there is no right child, right? Because when you apply the formula for the right child, it's 10, but 10 goes out of the bounds of the array. So we compare R with Q. So we compare R with Q, and QRST. So R is actually comes after Q, so that's why we won't do any move operation. So Q remains at this place because R comes after Q. So finally, in step number 4, we place R at index 4, and thus we have finished our dequeue operations. So I hope this makes sense. So this is different from the previous class in the sense that how the array gets modified, right? That part we can see. And you can see, on this side I have listed the steps. So what happens is you compare two children and then compare the maximum among the children with the candidate, right? And then you move as necessary, and you repeat the step. Keep on finding the maximum among the children, and then compare it with R, and then move. So once you're done, then you basically fill the hole with R, right? So R is the candidate. With the candidate, it found its rightful place. Okay, good. So I hope it makes sense. So let's see if you have any question. Okay, so let's move on. So we have seen NQ and DQ operation. Now here's a new question. If you have to search for an item in a heap, okay, so let's say you have a heap with n items. How fast can you find an item in the heap? Okay, so you might have a guess now. So heap is not designed for search. Okay, so an item that you're searching can be in any place in the heap, in the array. That's why it's a order n time. If when where n is the number of items in the heap. Okay, so search is not fast. Search is very slow. So if you have to search, you don't need a heap. You need a binary search tree or a sorted array. Let's move on. Okay, so the next question is a very interesting question actually, and it is asked in programming interviews. If you go for internship, you may get this question, so pay attention. So there are many answers, but there is only one optimal answer. Okay, there is one right answer. So the question says, write an algorithm to find maximum 10 items in a max heap containing many items. Let's say 1,000. It could be 10,000 or a million, but the problem is posed as top 10 items, right? So if we have a max heap, then maximum 10 items in the heap. So once we discuss the algorithm, then we'll look at what's the time and space complexity of such an algorithm. Okay, so the straightforward solution, you might have thought, build a heap of 1,000 items and then do DQ 10 times. If we do that, then we have the answer, right? So let's see. So what you could do is NQ, so the solution is NQ 1,000 items, in a for loop, pick an item, NQ it, and then DQ 10 times. So if we do these two steps, we have the answer. What will be the time complexity? Well, each NQ operation on a heap is log n, and we have 1,000. So we can say that if we have n items and NQ of one item takes log of n time, then the time complexity for building the heap is order n log n. Okay. Now we will see later that one can build a heap in order n time. Okay, so it's possible to build a heap in order n time, and we'll see that in sorting chapter. Okay, so here the catch is, when you are continuously adding items to the heap. So in the beginning the heap is actually small, right? It doesn't have all the n items that finally it will have. In the beginning it's 1, then 2, then 3, and so on. So uh, one could build a heap in a different manner rather than doing NQ 1,000 times or n times. So one could find a clever way of building a heap. So it could be done in order n time. So DQ, right? How fast could you do DQ 10 items? So let's say instead of 10 there is a constant called k. So k equals to 10, but k could be any constant number. So because each DQ operation takes log n time, so the time complexity for doing DQ k times is order k log n. Okay, so in total the time complexity is, let's say, order n log n plus k log n. Okay, this is the time complexity. So later on, as we saw, it could be done in n plus k log n. So that's the time complexity. How about the space complexity? Well, we need to store these 1,000 items in an array, so it has to have order n, all the items in a array in a heap. So time complexity is order n. Okay, so this is the most straightforward question, and I gave you an algorithm here using a heap because we are studying priority queue using heap. Uh, but 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 this is a motivation to do better, right? So can we do better? Can we actually, solve this problem using less space and even improve the time complexity, right? So that's what we will look at. So here the here the thing that you have to remember is this problem we have solved using max heap. So there is another kind of heap that is called a min heap. So let's talk about min heap. So what is min heap? So this is just a reverse of a max heap, all right? So min heap has to always keep the minimum element as a root. So, and if you remove the minimum element using DQ, then the next minimum should be the new root. Okay, so that's the idea. So if we use min heap, then it's possible to improve the space and time complexity. So that's the hint. So now I'll have a pause for some time about thinking about min heap and how one could do better. So let's see if you have any idea. Now it is counterintuitive because we are looking for maximum 10 items, and min heap will, min heap contains minimum element as at the root. So it's counterintuitive to even think about that min heap will solve the problem. So let's see. Let's see if we can do better. So let's say we put a constraint that the heap should be of size 10 because we need top 10 items. So you know let's make an array that represents a heap of size 10 only. So if you have like 1,000 elements, then we cannot store those 1,000 elements. It's the part of the array, but our heap will always remain uh, of size 10. So that means if we allow new elements to the heap, we may have to remove the existing element, right? So because the size is constant, it has to be 10. So since we have a min heap, we can do some checks and then check the root element of a heap and the new element and then compare them, and based on the comparison accept or reject the item. So that's hint at the second level. Okay, so let's see if we figure out the solution. So we will have a pause now. Okay, so here is the idea. We want to improve the space complexity, so we create an array of size 10 that will represent a heap. We enqueue the first 10 items in a min heap. Okay, so only 10 will go into the heap. Now for the rest of the items, that means 11th to the last, we are assuming we have 1,000 items. We check the root of the heap with the 11th item, right? So new item is 11th. If the root is less than the new item, okay? If the root node of a heap is less than the new item, then we remove the root, okay? And we add the new item. We add the 11th item, okay? So when we do DQ, the size of the heap becomes 9. And then when we enqueue, again the size of the heap is 10, but you can see that the smaller element, the root had smaller element when compared to the 11th item, so we removed it. If, now go to the else part, if the root is greater than the new item, then we reject the 11th item. Okay, and since it's in a for loop, you go to the 12th item and 13th item and always check, if the new item is greater than the root, then you remove the current existing uh, root node of the heap and replace it basically with the new item, right? So if you keep on doing that, what you'll end up is, the items that are smaller will keep on leaving the heap, and elements or items that are larger will, occupy the heap, will be there in the heap. So in the end, after you go through all the 1,000 items, you will have a heap that has maximum 10 items, right? So it's wonderful that you had a min heap, but by selectively accepting and rejecting the new items, we were able to make a heap that has 10 items, and all of them are the maximum 10 items. Okay, so I hope this makes sense. So here is an example. Let's say the first 10 items, I build a min heap using the first 10 items. So among all, you see the minimum one is at the top because it's a min heap. And let's say the new item, the 11th item, is 1. So when the new item 1 comes, you compare with the root 3. So 1 is less than 3, so 1 will never be a part of the maximum 10 items, as we can see, right? So we reject it. Now how about if the next item, if the 12th item is 8? So if the 12th item is 8, now you see that 8 is definitely greater than 3, so 8 may be a part of the maximum 10. So we remove it and we NQ8. Okay, so the first item gets rejected and NQ8 will be accepted. Okay, so this example I hope makes sense. So we keep doing that with 13th and 14th and 15th, and we repeat this for all items, and we'll end up with a heap that contains the maximum 10 items. Okay, so now the next question is, I have a habit of asking what's the time complexity. So what's the time complexity of the algorithm that we just discussed, right? Because we saw that n log n plus k log n was the time. So I mean, if you go back, and since our heap will never have more than 10 items, so we definitely saved some space in the heap, right? So the input always contains 1,000 items. We cannot improve that, but we can improve how much space our heap takes, and now we have a heap that only has. So space wise, you can see we have saved space. How about time? So let's look at the time complexity of this uh, algorithm that we discussed. So input array is ARR, and you have to find top 10 items. So here it's K, right? Top K items or maximum K items. So you create a priority queue using a heap, and you are creating, you're giving a size here that my heap should be array of size K. And the top, I mean, the first K items, you basically enqueue it, and it will build a min heap after this step, right? And here you go through the rest of the items. You have to compare the new item with the root node. So you get the root node using DQ. If there was a peak operation, you could have directly done peak operation, but we have not seen peak operation. So we remove it and see what's the root. We call it top, and then compare the top with the new item. So if the new item is greater than the top, then we enqueue it. Okay, if it's smaller, we basically reject it. So when we reject it, since we have already removed that item, so we enqueue it again, right? So we enqueue the top. So we go through the all the items, and in the end our heap has k items, so we print all of them, right? So what is the time complexity? Well, this step, the first for loop, is k log k, and the reason is the size of the heap is k, right? So the NQ and DQ operation will be of time log k. And since there are k, this happens, the NQ operation happens for k times, so it's k times log k. So the first part is k log k plus the remaining loop essentially runs for n minus k times, right? Where there are n things. So I'm typing it here below. Let me make it slightly bigger. And then you have, a DQ operation and NQ operation. So it's like 2 times you are doing, and it's log n minus k. So n minus k is usually very small. I mean, as is n minus k is as big as n. Okay. So in bigger notation, because you're concerned with the upper bound, so it suffices to say remove this k. So, and it also, you could remove the exact count. So it's n log n. Okay. So k log k plus n log n, right? So we have actually saved here. So in our previous approach using max heap, we had k log n, and now we have k log k, right? So essentially, the k term is very small. So this is this has this does not carry a lot of weight. The time is mainly determined by n log n. That means the rest of the queue. Okay, I mean the rest of this for the for loop here. All right, I hope this analysis makes sense. So you could add an order notation here. Okay, so this is the time complexity. Now let's go to the next slide. So since we saw an algorithm, right, you could apply that to 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 this input. So here you have an array that contains certain numbers. So this is the ARR array, and k is 3, right? So we saw ARR is the array and k is 3, right? So you apply this algorithm using this input, right? If you do that, what gets printed? What is the output? Okay, so let's pause, and you could think about what gets printed. Okay, so I hope you have thought about. It would take more time than this if you if you apply all these numbers to this algorithm. It will take some more time, but in the interest of time, uh, well, this is supposed to give you the max uh, k numbers. So the top 3 numbers are 10, 9, and 8, and that's what you will get. So you could work it out as as homework, right, for practice. So initially you have these 3 numbers 6, 7, 3. You do NQ operation. The heap size is 3, so the heap would look like 376. It's min heap. But once you have processed all these items and selectively accepted, rejected some items, you'll end up with the maximum 3 numbers. And it's a min heap, so minimum 1 has to be on the top. The rest order we cannot guarantee, but you get the maximum 3 numbers. Okay, good. So I hope it makes sense. Let's see if you have any question. So okay, good. So we have finished here. So now we will look at sorting. Okay, so the next chapter is sorting. We have finished priority queue. We'll look at elementary ways of arranging numbers in certain order. Ascending order, like 1, 2, 3, 4. That's the order we will look at. Okay, so let's go to sorting. Let's stop now.